Okay, welcome. This is ACT Worksheet 207, Circles and Conics. As you take the test, you'll see 1 to 2 problems on circles. These are traditional circle problems, like area of a circle is pi r squared, or circumference of a circle is pi times diameter, or some people prefer circumference is 2 pi r. Same thing, two times the radius is the same as the diameter. So you'll get about 1 to 2 of those a test, and I'll show exactly what that looks like and how they tend to appear through past problems from previous tests. And then conics, you'll get 1 conic problem a test. A conic is either a circle graphed in an XY coordinate plane. So it's a circle that's graphed, and it has a standard equation for it. Or it can be an ellipse, and I'll show you what they may ask about an ellipse. Occasionally, it will be a hyperbola, but I've only seen a hyperbola once on the test, and there's a way to get it without really needing to know much about hyperbolas. So we'll leave that off in this video. Okay, well, anyway, with that said, let's talk about circles first, and then on the second half, we'll make our way into conics. So we know a circle is 360 degrees. We know circumference is 2 pi r, or pi d. We know how to get the area. A big part of circle problems is this concept. I'll show it right now, and then we'll see how it applies to the test. But often, you'll be given a circle, and you may be told, okay, we have an angle, and let's just say that our angle is whatever this is. So we don't know what the angle is. Let's say it wants us to figure out the angle. Okay. And they may say, hey, guess what? Our radius is 6, and and let me see how I want to do this. I have a couple ways I can go about it. I'm just trying to think about the best way. Okay, so they may tell us that this sliver, this shaded region right here, so this in red, the shaded bit, it wants to know the angle, so angle question mark. But the shaded bit in red may be, we'll say, 4 pi. So the question is, how do we figure out the angle knowing that the shaded bit is 4 pi and that the radius is 6? And if you want, you can pause it and try to do it. But the typical construction, when they give you something like this, whenever they give you the radius or the ability to figure out the circumference or the area, you kind of want to treat it as a part to whole situation. And what I mean by this is you always know the degrees. So you always know the whole for degrees. So 360 is the whole way around the circle. We want to know the question mark. I'll put question mark here. And then we're talking about area. And with regards to area, the part of the area we have is 4 pi. And we know that pi r squared, right? Pi r squared is the whole area, so 36 pi is the whole area. So now we can easily figure out the part, right? So this here becomes just reduces to 1/9. And then this is pi over 360. So really, if we were to figure out what the question mark is, it's just 1/9 of the whole thing, right? It's 9. I'm just going to call the question mark x now, just to kind of keep it in algebraic form, equals 360. And 360 divided by 9 is going to be 40. So we'd say, okay, that's going to be 40 degrees. Very common type of problem on the ACT. They'll give you the radius, and they'll want you to either figure out an angle of a slice, or they'll want you to figure out maybe the angle of an arc. They'll give you a few pieces, and you need to use the area or circumference of the circle to figure out what you don't know. And I'll show you another variation on that in just a moment. So anyway, that's important. Knowing that if you draw out from the center of a circle, you can always quickly create an isosceles triangle comes into play. Very important to know that when you draw a line tangent or just touching a circle, and you draw a line from the center to that line, and that creates a 90-degree angle, so you can easily create 90-degree triangles or right triangles. Also, if you take the two ends of a diameter and you draw them to any point on a circle, that always creates a 90-degree angle. These are all, I know there's a bunch of triangle rules that were learned for GCSE, so I know these are probably all fairly familiar. Another interesting rule is that if you were to draw a circle and you create a central angle, so in this case, we'll just make it 90 degrees, and you pick any point beyond that, so I'll just pick this point right here, and you go from the same 2 points that you started with, and you extend to the point not in the center, but on the circle. If this is x divided by 2. It cuts in half because it stretches out, so the angle narrows. This last one is more kind of theoretical, or not theoretical. It's something that if you want to look at it for fun, it's kind of cool. If you have 3 circles that are all tangent and you go to kind of touch their centers, you can always create an equilateral triangle. Because if you think about it, this is a radius and this is a radius. As long as these circles are congruent, meaning the same, this is a radius, this is a radius, this is a radius, this is a radius. So we know these to be 60 degrees. I haven't really seen this concept come up on the test, but I've seen it come up enough with circle problems in general where I felt I would include it here. But anyway, let's just dig right into this packet. Picked some commonly missed problems. So this first one, 11, isn't commonly missed, but it has to do with what we were just doing a moment ago. So if you want, pause it, give it a shot. I'm just going to keep on rolling though. So the shaded sector of the circle shown below is bounded by radius AO, right here. Should probably do that in a different color. And radius BO, body odor, that's not a good radius, and minor arc AB. The length of AO is 4, and the area of the shaded is 6 pi, so this is 6 pi. What is the measure of AOB? Okay, so if we want, this is actually kind of identical to the one we just did. I probably should have picked a problem slightly different, but anyway, if we think about it, we always go part to whole. And we always know with degrees that we have 360 degrees. So with any circle problem, if we're trying to figure out a piece that we don't know, we can always use the idea that we have 360 degrees as a whole. We want to figure out what the measurement of this angle is. So I'll just put x for this angle. And then what we do know is we do know that the whole area is 16 pi. And we also know that the shaded bit is 6 pi. So this is going to reduce to, 2 goes into each of these, so it's going to reduce to 3/8. And we're going to end up with 8x when we cross multiply. 3 times 360, so 720, 1080. 1080 divided by 8, and I know you'll have a calculator. Goes in 2 times, or 2 times, what am I saying? Let me erase that. It goes in 1 time to 10. That's a 2. 28, 3 times. It's a 24. Bring down a 4. Or bring down the 0. 8 goes into 45 times. So that degree measurement is going to be 135. Okay. Let's keep on rolling. We'll do a few more circles. I think one more circle, and then we'll move on to conics. I'm going to skip 15. All right, I'll do 15 real fast. Pause it if you want to try it yourself. I'm just going to do this real fast because I find a lot of students get stuck on it. It's not necessarily a common problem, but it's one that has come up on the past tests, and I find students have difficulty with this one. So in the figure below, the vertices of rectangle BCDE lie on the circle. Okay, so we've got BCDE. And the vertices of the rhombus are the midpoints of the sides of the rectangle. So these are all the midpoints of the rectangle. So they cut the rectangle in half. They cut the sides of the rectangle in half. And point A is at the center of the circle, rectangle, and rhombus. The radius of the circle is 4 How long is the side of the rhombus in feet? Okay, so we know the radius of a circle is 4. So from A to C is going to be 4. Okay. So if you know that that's 4, you can probably take an educated guess at what GH is. I mean, go ahead and take a stab. If this is 4, this looks like it's definitely more than half. It's definitely not double. I don't think that it's 1.5 times as much. So you're really down to B or C, and you could kind of measure. I mean, I would guess C just based off of that. But if you want to know kind of mathematically exactly how we know the answer is C, so the correct answer is actually C as well. If you just make a rectangle out of this, these are the two diagonals of the rectangle. So one diagonal of the rectangle is your radius. The other diagonal of the rectangle is the side of the rhombus. And it wants to know how long is the side of the rhombus? Well, it's the same length as the radius because it's just the other diagonal. But again, figures on the ACT, you can't assume that they're drawn to scale, the test says, but I find that they're always drawn to scale unless stated otherwise. Don't hold me 100% accountable for that, but if you're stuck on a problem or not sure how to go about it, then why not use, what I'm telling you to give you the best shot at getting it right. So I always kind of assume if I'm stuck that figures are drawn to scale, unless stated otherwise, even though the ACT tells you you can't make that assumption. And I know you couldn't make that assumption on A levels. They purposely don't draw them to scale on A levels and GCSEs. We're going to skip 23. And we're going to go to, did I skip the one I wanted to do? We're going to go to 24. All right, this problem stumps a lot of people. Again, feel free to pause it and give it a shot. Otherwise, just stay with me right now. So in the figure shown below, C, M, N lie on the circle whose center is right here. And MON is a right angle. What is the sum of the measures of CMO, so this angle, and CNO, so this angle? So it wants to know this angle plus this angle. You're not going to be able to get either of these individually, but here's how you figure this one out. I'm going to show you two ways. You can always draw from the center of the circle to create an isosceles triangle if you create two radii. So this and this are both radii, so that's an isosceles triangle. This and this are both radii, so that's an isosceles triangle. So the interesting thing here is we have 360 degrees. We can take away 90 degrees from that 360, and we're left with 270, right? The 270 degrees that we're left over with right here have to divide between these two. I mean, so we can just cut this 270 degrees any way we want. Looking at this, I would say maybe, I don't know, we'll call it this angle right here. We'll call this 160 degrees, and we'll call this 110 degrees. Okay, so when we call that 160, let me do that better so it's easier to see. So if we call this 160 and this 110, then that means that 70 degrees, right, because this is a triangle, gets split between the two other angles of this isosceles triangle. So this is 35. This is 35. This one, 20 degrees, gets split between these two on this CON isosceles triangle. So this would be 10 degrees, and this would be 10 degrees in order for all three angles of that triangle to add up to 180. So this angle plus this angle is going to be 45. And feel free to split that 270 between these two angles any way you want. You're still going to get 45 as your answer. So that's one way to do it. Another way to do this problem is, if you know that this is a quadrilateral, I know the CMON is a weird looking thing, but it only has 1, 2, 3, 4 sides there. So because it only has 4 sides, we know that it has to add up to 360 degrees. And we know that this is 90 degrees, so angle C is going to be 45 degrees. Remember, if that rule we went over earlier, if you draw to the center, it creates an angle. If you draw beyond the center to any point on the circle, it creates half that angle. So that's 45. If 360 is our loop around this whole thing, and we take away 90, we have 270. So then we're just left with these two angles. I'll call them angle M and N. and we want to know the sum of m and n. Well, we're just taking this, which is 315, subtracting it from 365, and we have 45 equals the sum of m plus n. Awesome. So 2 ways to get that problem. And that was like one of the last 10 problems on a test. So it's considered a harder problem. All right, so let's kind of move on. Let's talk about conics here. So you're going to get one of these problems a test. They're fairly straightforward once you know these 2 equations. So if you had this equation for, let's say, a line, a linear equation, y equals mx plus b or mx plus c, you know that this represents the slope and that represents the y-intercept just by looking at it. Well, the standard equation for a circle, you have an x squared, a y squared, and an r squared. So just by looking at this right here, we know the center is at 10. So whatever is next to the x in brackets, it's minus h. So in this case, our h would be 10. So it's a positive 10. It's plus 3. So our k must have been minus 3 to make it plus 3. So that tells us our center is at 10, negative 3. And if you take the square root of our radius, that's 9. So that's where our center is right there at 10, negative 3. And then our radius is 9. So we can graph this circle. What I'm going to do right now very quickly, and you can fast forward the video if you're not interested, is I'm just going to show some very quick theory behind this because I think it's kind of cool. So this equation comes from Pythagorean theorem, right? A squared plus b squared equals c squared. Well, watch this. Let me just draw a circle. I'm going to put this point on the circle. I'm going to draw this right here. So I'm going to make this point right here 3, 4. Okay. So if I make that point 3, 4, we have a 3, 4, 5 triangle. So we know our radius is 5. Well, if I were to write the equation for this, it would be x, and because our center is right at the origin, it would be x minus 0 squared plus y minus 0 squared equals r squared, so 5 squared, so 25. Well, the cool thing is any point on the circle should make the equation balance. So if I put in 3 for x and 4 for y, and I'm sorry if this is a little hard to see. Oop. All I'm getting is 3 squared plus 4 squared equals 5 squared. So it does balance. Essentially, this equation comes from Pythagorean theorem. And the interesting thing is if I were to take this same exact circle that we made, and I were just to move it all the way out to here. So same exact circle. I'm going to move it to here. Still a 3, 4, 5. But I'm going to put the center now at, just going to say the center is 20, 0. So this point right here is going to be 23, 4. Well, if you think about it, the equation for this circle is going to be x minus 20 squared plus y minus 0 squared equals the radius squared, so 5 squared. Well, if I put in the points I have, I would have 23 minus 20 squared plus 4 minus 0 squared equals 5 squared. Well, I end up again with just 3 squared plus 4 squared equals 5 squared. So all the minus 20 does is it just gets rid of the distance from here to here to turn this back into Pythagorean theorem, right? Where it just gets rid of this distance so that the 23 turns back into a 3. And we're looking at Pythagorean theorem again. Anyway, if you think that's cool, then great. If you're like, I don't need to know that to be able to remember this equation, that's fine as well. You don't necessarily need to understand the theory. I just thought I would show it. Okay. So then with an ellipse, the equation reads just like the equation of a circle, where you have x minus h squared plus y minus k squared. That's telling you your center. So our center is at -7, -5. Okay. But the big difference with an ellipse is it's always going to equal 1. Okay. And this will always be a plus. And your denominator tells you your major and minor axis. So how far your ellipse stretches along the x-axis and the y-axis. So let me zoom out to kind of show how this plays out. And I'm sorry if you're like, hey, Dan, I didn't sign up for an eye test here. But if you look at this right here, this equation and this ellipse, we go -7, right? -5 based off of the top. So here's our center. And because below the x is 81, that's your a squared. If you take the square root of that, that's 9. That gets you your major axis. So our major axis here is 9. And we know it's along the x because it's below the x. Now below the y, we have 4. That's our b squared. So you take the square root of that and you get 2. And that gives you your minor axis. So that's how you read the equation of an ellipse. The center is in the top. The bottom tells you the distance for your major and minor axis. And if you think about it, it's kind of cool because, like, if I were to give you the equation of the circle earlier, we could even put it in ellipse form. So, like, if we were to divide everything by 81, I would have x minus 10 squared over 81 plus y plus 3 squared over 81 equals 1. So I just put this circle equation into standard equation into ellipse form. I made it equal 1 with the denominators, but because the denominators are the same, you can see that your minor axis and your major axis are both 9. So we're going down 9, right, because of that, and we're going over 9 because of that, right? Our a squared and b squared are both 81. So essentially, that's kind of how you can toggle between a circle equation and an ellipse equation. But anyway, let's look at 2 problems real fast. So 32 is not hard if you're willing to acknowledge, wait a minute, I have something that's in an XY coordinate plane and they didn't give me anything to look at. So instead of trying to think about this in your head, which would be absolutely a difficult task to try to figure out, just put it in front of you. If you can read these equations, put this right in front of you. So pause it and kind of say to yourself where this circle is and what the radius is and where this ellipse is and where the radius is, and see if you can plot it out. Anyway, I'm going to keep on going. So they want to know at how many points do these 2 things intersect. So if we do the circle, we go 4 to the right, up 3. And our radius is 2. So something like that is our circle with a radius of 2. So this point right here will be 5. Okay, so now if we graph this ellipse, we go over 4 and up 10, so somewhere like up here. And our minor axis is 2. So it looks just like the circle there. And then our major axis is 4. So we go down 4 to 6, up 4 to 14, right? And that's our ellipse. So these do not cross, right? Because if you think about it, our major axis from the center goes down 4. That only gets us down to 6. Circle only goes as high up as 5. So that one becomes really simple if you're just willing to map it out. Okay, one more problem. All right, so I picked this problem because I don't mention the foci in the notes. This problem comes from, I think, April 2017, that ACT, or one of the ones from 2017. Interestingly enough, April 2021 included foci for the second time. So I'm going to give you 2 ways to get this. First, I'm just going to tell you the answer. It wants to know the foci of this ellipse. The foci are here. It's at 9, or not 9, sorry, 3, 9. and at 3, 1. So I'm just telling you the answer is D right off the bat. I'm telling you the answer because it's going to help to explain what foci are. So first off, foci are not on the ellipse, okay? They're not on the ellipse, and they're also not the center of the ellipse. So just by knowing that, what foci are not. They're not on ellipse, and they're not the center of the ellipse. So just by knowing that, the only answer that can work here is going to be D. Right, 0, 5 is on the ellipse, 3, 0 is on the ellipse, 3, 0 is on the ellipse, and 3, 5 is the center right here. Right, we know 3, 5 is the center, not just by looking at it, but from this. -3, 3 to the right, -5, up 5. Okay, so now I should actually tell you what foci are. So foci have to do with kind of the center of gravity. It's kind of interesting. If I were to draw this and this, from here, this is A, this is B. If I were to pick any other point on this ellipse, so this one and then this one, this is C and this is D, A plus B, the sum of A plus B will always equal the sum of C plus D for any ellipse. So wherever I move on the ellipse, if I draw 2 points and I draw to the foci, the sum of these two will always equal the sum of those two. So it has to do with the center of gravity, but the way that you can calculate an ellipse, if you want to remember it, again, it may just be extra information. You may just need to know the knots. That an ellipse is always on the major axis, so the ellipse is always on the major axis, and it's not the center, and it's not on the ellipse, but it's always on the major axis. So foci, always on major axis. But here's how you calculate it. The way you calculate it is you take the square root of the difference between the higher and the lower denominator. So in this case, that's the square root of 16, which is 4. Once you have 4, you go from the center along the major axis up 4 and down 4. And that gets you these 2 points. So that's technically how you calculate the foci of an ellipse. Okay, I hope this video has been helpful. Good luck with circles and conics. As I said, that knowing the stuff on this worksheet will get you about 3 out of 60 problems every test. So it's good to have those 3 in the bank. Okay, well, good luck, and always come back for any other videos or concepts.